Thanks very much for giving me the opportunity to present about the status of CART, the Changing Atmosphere Infrared Tomography Explorer, which is currently a candidate mission for ESA's Earth Explorer 11. So, one second, how do I just press that, right? Earth Explorer 11 is one of ESA's flagship science mission. To be launched in 31-32, around that framework, and currently we are in a competitive phase 0, so there are in total 4 missions competing. That's CART, the mission I'm talking about here. The other missions are, one other is Nitrosat, mapping reactive nitrogen at the landscape scale. And then 2 radar missions, Seastar measuring small-scale ocean dynamics, and Wyvern observing winds, clouds, and precipitation, another radar mission. But for obvious reason, I'm not talking much about, or nothing at all about these other missions, but focusing on CART. What we want to do with CART is essentially investigating the interaction between circulation in the middle atmosphere from the upper troposphere to the lower thermosphere, the interaction between circulation composition and the impact on regional climate change. And I don't need to tell you here, we have lots of evidence, either from recent observation or from climate models, that there is evidence for profound changes in the atmosphere throughout its whole depth, so not confined, obviously, to the lower troposphere, but throughout the stratosphere, mesosphere, into the thermosphere. We have evidence that the large-scale, this wave-driven large-scale circulation is changing. We don't really understand how in detail this wave driving is changing. That has implication then obviously on transport and mixing of species, which with important impact on atmospheric composition, the coupling with the upper atmosphere, for example, here the subsidence of nitrogen compounds from the thermosphere into the stratosphere provides a coupling mechanism between the upper atmosphere, space weather, and the middle atmosphere. And all of these have impact on surface climate. And only in recent years, I would say, we are fully appreciating these coupling mechanisms, how the middle atmosphere impacts on regional surface climate. And just to highlight one study that I found particularly interesting is, for example, this one. I've been showing that a number of times already because I find that really very interesting indeed. That how the Australian hot and dry extremes are induced by weakenings of the stratospheric polar vortex. And this paper, just by coincidence, came out in late 2019 at a time when there was, and they couldn't predict that obviously in that paper, at a time when there was a very strong weakening of the Antarctic polar vortex, and that was indeed followed by some hot and dry extremes in Australia that led to these very large wildfires there. And the other surprise, and we heard about that here a number of times in this workshop already, was the lifting of these wildfire smokes very high in the stratosphere, up to 35 kilometers or so, that we didn't expect before that could happen. And so we have more and more evidence how the middle atmosphere is connecting with the troposphere, with surface climate, and providing feedback mechanisms that we don't fully understand. So that motivates us that we are convinced that we definitely need another mission, another LIMP mission that addresses these questions of the changing atmosphere throughout the whole depth of the atmosphere. And the specific objectives that we have for the proposed CART mission are that we want to diagnose the atmospheric large-scale circulation through long-lived trace gases, and in particular age of air, from the upper troposphere to the lower thermosphere. We want to quantify the gravity wave momentum flux, the direction of the gravity waves, and the gravity wave driving of the circulation, because that is so far not well constrained at all in observation. We heard a bit about atmospheric gravity waves this morning already. We want to investigate the coupling with the upper atmosphere and space weather, in particular by following the descent of nitrogen oxides from the thermosphere down into the stratosphere and see what they do with stratospheric chemistry, heating, and so on. We want to focus then, that provides kind of the upper boundary. We also want to look at the lower boundary of the middle atmosphere and detect the pollutants and aerosols in the upper troposphere and stratosphere, as I've shown from wildfires, but also in particular from volcanic eruptions, in particular focusing on the sulfate budget in the stratosphere, and all of this together, so to say, attributes and changes in upper tropospheric and stratospheric ozone, water, and the feedbacks on surface climate. Now, this picture may give you the impression that everything is very nicely zonally symmetric. You know, it is not. And this is a very important part of the atmospheric circulation, that we have a lot of fine-scale structure, filamentary structure, mixing. Mixing is an important process of the large-scale circulation. And this is just one figure here from, actually it's done from ECMWF reanalysis of ozone at 100 hectopascal, just arbitrarily, just to give us an idea to appreciate. And it's actually an animation, but I don't know how to start that. What happens if I press there? Then it's gone. Anyway, I can't get that run in the moment. Doesn't matter. I mean, it gives you an idea of this stirring and mixing. That's an important part of the large-scale circulation that we want to address there. And in particular, or one example of that is here just one snapshot from one of our aircraft campaigns. So Wolfgang already before the break gave an idea of what is possible with this aircraft data. Ozone measurements, this is actually from an in situ sensor. That's about a 2,500 kilometer or so flight at 14 kilometer altitude, basically constant altitude, but you see a lot of variability there in the ozone that is also reflected in things like age of air. In this case, it was deduced from in situ measurements of SF6, N2O, and other long-lived trace gases. And the red curve are the actual in situ measurements, and overlaid on that in black, thick and thin curves are 50 and 100 kilometer averages over that, to give you an idea of the scale of the things. And it's really at the 100 kilometer scale that we want to aim with care. So resolving these things that so far were possible only with aircraft campaign data or so on the global scale, to get a better understanding of the overall circulation and processes in the atmosphere. And how we will do that, the technique for that is infrared limb imaging. So we will have simultaneously we will observe the limb on something like a bit more than 100 kilometer vertically, 5 to 115 kilometer, roughly 400 kilometer across track, with something like, say, 128 pixels in the vertical, and then some pixels binned in the across track dimension, say 16 pixels or so, 50 kilometer resolution across track. And by doing that along the track as a satellite flies every 50 kilometer, we can then combine these and do actual tomography, so that we are aiming at getting observing the 3D structure of the atmosphere on a 50 by 50 by 1 kilometer scale. So, I just said nominal sampling 50 by 50 by 1 kilometer. And on the left-hand side is one example how CAD may see a temperature fluctuation from a gravity wave that's excited by the flow over the Andes of South America. So you see the temperature fluctuations associated with gravity waves that we can get then here with a vertical coverage 5 to 115 kilometer. And in particular, because we will do that with a Fourier transform spectrometer, that's the idea behind that, with a spectral range from 710 to 2200 wave numbers, so that's about 4.5 to 14 micron or we are aiming at something threshold here, 0.2 wave number resolution, we get full spectra for each of the pixels. We are for a sun-synchronous orbit in loose formation with METOP second generation, so that we can have synergies with the many Nadia sounders that are on these satellites, on the operational METOP satellites. So from the Fourier transform spectrometer, synthetic spectra, what we expect to find look like this here, just a few selected targets that will be relevant in the different wavelength regions. So the long wavelength part is essentially important to get CO2 for the temperature information. Here the shorter wavelength part is important for CO and NO, which are very important to study the coupling with the upper atmosphere. But CO is obviously also very important in the UTLS for observing pollutants, biomass burning, and so on. So the range of parameters that we are expecting is pretty large. Not all of these are primary species that are specifically in our focus, but we are very confident from the aircraft instruments or other heritage instruments that these parameters can be achieved. That would be temperature over this really very large altitude region, but also ozone and water from the upper troposphere to the mesopause region, essentially long-lived traces like methane, N2O, SF6 to diagnose changes in the atmospheric circulation. Then we have here CO, NO, NO2, which are very important for the coupling with the upper atmosphere and space weather. I'm showing some examples on that in a moment. Then we have a whole range of nitrogen compounds, chlorine compounds, brominitrate as well, but brominitrate is difficult, but halogen compounds in general to study ozone chemistry and changes in chemistry in the middle atmosphere. Then we have a range of pollutants like PAN, ethane, and so on, plus also CO, which was already here earlier in the list, important pollution traces. We have aerosol precursors and aerosols itself, SO2, H2, SO4. I will show some examples from some studies we recently did. And we also get information on clouds like polar mesospheric clouds, polar stratospheric clouds, and cirrus clouds. So far we are in phase 0, so doing a lot of performance estimates and theoretical studies and so on. And we have, for all of the parameters that I showed to you, we are doing this kind of performance estimates that I'm showing here, just one for ozone as one example. So in these different colors are our goal performance and the threshold performance from a scientific side, and then the black lines or the lines are the estimated performance from some theoretical retrieval studies. So with ozone we are getting a vertical resolution that is between 1 and 2 kilometers throughout most of the altitude region, at a horizontal resolution that is up to 50 kilometers or so, that is 100 kilometers horizontally, and we investigated a lot of the different systematic and random errors, and the total error we estimate is something like in the order of 20 ppb or so in the upper troposphere, and then getting a bit worse, something like 100 ppb throughout the stratosphere. But of course that is, we can't put all of this information here, lots of plots, so we developed an overview that shows for the different parameters that we have relative to the science requirements, where we are well below threshold, where we are at around threshold, that would be yellow here on this traffic light, and where we are above threshold, and it's essentially only for CO during nighttime conditions in the thermosphere that we will not meet the our science threshold. Everything else, the performance looks very nice. But I mean, to fully appreciate that, I think it would look. I mean, this probably tells you more. That is here a comparison between a model, WACAM-X in that case, for two examples, temperature and ozone. The model is on the left side, and then the expected CAD performance on the right side on one example orbit from the South Pole through the equator over the North Pole, and then on the other side down the orbit down to the South Pole again. And we can play the game, spot the differences here. I mean, it's at least on this scale, it's difficult to see the differences, which means expected performance is really excellent there. That contains all the noise error, calibration error, systematic error. You see, for example, here for ozone in the mesopause region, you see some resolution degradation that is evident, but from this, I mean, very nice performance we expect. But what does it mean for our science cases, for our science codes? And for example, here I've shown this figure of the gravity wave case before, just to remind you that we are not just seeing everything just on one orbit, but we are having this 3D capability also find scales across track, and from that Peter Preuss and his team is working on demonstrating how we can extract gravity wave information, gravity wave momentum flux and drag on that, and there's a poster by Jörn Ungermann. I don't know if it's up today or on Thursday, but there are more details given for that. So for example, here on the top plot on the left-hand side is the gravity wave momentum flux at 20 kilometer, how CARD would see that on the orbit, and that is the bluish and reddish colors there, and the green shading below is the zonal wind from ECMWF. So the basic message, and that's centered on the North Pole if you can't see the map below. So the basic message here is that it's the excitation of the gravity waves on mountain ridges, on whatever, on the sources, but also the propagation conditions for that the wind needs to be in the right window, so to say, for the gravity waves to propagate, and then where they deposit their drag on the right-hand side at 30 kilometer. For example, you see here a hotspot of the deceleration, 10 meter per second or so per day. And then it's in zonal means compared to truth is ECMWF, or the model that has been run here for this test case, and then the CARD data extracted the momentum flux and the drag, the deceleration here, or acceleration and deceleration of the wind on the right-hand side. So showing that this matches that really very well. So we can have can really derive this quantitatively through the CARD observation. Another science case here is the observation of NOx in the thermosphere. So similar plot as before, WACAM on the left-hand side, CARD on the right-hand side. This is now for two different cases. For geomagnetic quiet case, 27th of October on the top, and 31st of October, that is more active on the bottom. And so the scale is now, the vertical scale is now from the mesopause ascent, or from the upper mesosphere up to 150 kilometer. And you see essentially that what the model says, the NO would be the NO density, that can be very well reproduced by CARD. And what then can be done in combination with traces like CO is to derive also quantitatively the flux of this enhanced NO, or the NOY, into the stratosphere. That is a figure here at 50 kilometer altitude. On top, the model, the WACAM model, the bottom row is CARD, and you see the actual NOY, but also the separation into the background and the EPP, so energetic particle precipitation, enhanced NOI, that has been done in a similar way as described here by Bernd Funke's older paper, by using correlations with CO. So again, we are very confident that we can, with the data quality, address this science here. In the UTLS region, we can profit quite a lot from both previous experience and campaigns with the Gloria instrument you heard about before earlier today. And we are also, as part of the ESA studies here, the phase 0 studies, we're doing campaign activities with Gloria. So the measurement principle is very similar. So you have this limb image, and then for each pixel have the spectrum. You've seen earlier a picture of Gloria on halo. Here's one in South America, and Gloria mounted below the fuselage of the aircraft in this belly pod. And one example here from one of Søren Johansen's papers is biomass burning or PAN, peroxyacetyl nitrate observations on this transfer flight here with strongly enhanced PAN in the off the coast of Brazil, which was at that time heavily biomass burning influenced, and this observation we are now trying to replicate with our CART simulator. So on top is the observation of PAN, the strongly enhanced PAN here in the UTLS by biomass burning. This in the middle is what the CAMS model tells us. So what the CAMS model predicts or calculates for that, which agrees overall pretty well. By the way, these white areas here in the observations are where there's cloud contamination. The white areas here are where the ECMWF or CAMS model tells us that where clouds are, which kind of nicely matches. And then here in the bottom figure, we are seeing how CART would see that. So including the limited resolution and the random and systematic errors, and you see that agrees pretty nicely. And also the ideas where it will be possible to observe because of clouds and where not. On the right-hand side, similar, the same situation, but now projected at 12 kilometers in the background, CAMS model, and then overlaid the CART orbit, and the red track here is the Gloria flight path. Another situation we are looking at here in phase 0 is how well can we constrain the stratospheric sulfur budget. For the example of the Raikoki volcanic eruption here, again a similar situation. This is SO2 a few days after the eruption on the left-hand side. The CAMS model, you see all this nice filamentary structure, how that's moved around, and on the right side, on the orbits of one particular day, how CART would see that. The very interesting thing about the infrared observations, like CART can do that, is that we can not only measure either SO2 or aerosols, but both SO2 and the H2SO4, so you really can combine them to get the budget of sulfur in the stratosphere. And this here is similar as plot before, but this time for H2SO4. And then if we combine them, this here is for different days after the eruption, the zonally integrated amount of sulfur from the CAMS model that we take as a synthetic truth here, and then how CART would see that. And you see that the first days after the eruption, the satellite doesn't capture the full amount, just because it's not dispersed very much, and just between different orbits, for example. But then from a few days afterwards, the total amount of sulfur is very well captured by the model. In particular, as we have SO2 and H2SO4. We heard already this morning the need for limb observation to better constrain tropospheric columns by limb nadir matching. That is something that we are exploring for CAD also to quite some detail, and it's a motivation why we're proposing to fly in loose formation with METOP second generation. Excuse me. And so that's the general sketch how that would look like. So as CAD flies along here doing this limb observation, ideally we try to match that with the IASB observation on METOP second generation, and then can combine them. And that not only provides additional information for ozone and other trace gases at altitudes below, you get information with the limb sounders, but Piera Raspolini and her team did a nice study, and there's a paper, the poster on that, dedicated to that also in the UTLS region, the combination of limb and nadir improves the retrieval relevant relative to the pure limb observation. For example, that is here the reduction in the total error of limb and nadir compared to just the limb observation, so quite a lot of reduction in the error. Vertical resolution is not improved so much, but the horizontal resolution is improved there. So I don't know how I'm doing time-wise. I'm probably a bit fast, but that gives us more time then. So because I'm already coming to the summary of what I've shown, so with CAD we're aiming at the first comprehensive global 3D tomographic measurements really of the processes from the troposphere to the lower thermosphere at something like this 50 by 50 by 1 kilometer resolution, and that is crucial really, because then we could really quantify from these high resolution measurements the gravity wave momentum flux, its phase speeds, and the drag for the circulation, and at the same time we can quantify the overall large-scale circulation by measuring these long-lived traces that will provide us age of air and other diagnostics, also down to the mixing scale, or down to the 50 to 100 kilometer scale that are shown as the example from the aircraft data that are relevant for mixing processes. We will have continuous observations into the lower thermosphere, look at the coupling there, and at the same time observe pollutants in the UTLS, and in particular have a focus on the budget of sulfur in the stratosphere from SO2, H2SO4 aerosols, and OCS, which I haven't talked here much about. And I just mentioned flying information with METOP second generation will provide synergies with IASB and Sentinel-5 for measuring tropospheric composition. So what are the next steps now? As I said, CAD is currently in undergoing phase 0 studies, so we are devoting quite some efforts on performance estimates, but also looking at science impact for that. We have the gravity wave studies I already mentioned, and I encourage you to look at the poster by Jörn Ungermann for that specifically. For the limb-nadir synergies, as I mentioned, Piera and colleagues have a poster on that, and we already started some impact studies of assimilating CAD observations to study the stratosphere-troposphere exchange and the flux of stratospheric ozone into the troposphere, and first results of that will be just given in the talk right after that by Quentin Herrera. So where do we stand with that? We are currently preparing material for the down selection by ESA. There will be an open user consultation meeting in Bucharest on 10th, 11th of October 2023. So if you want to come, you're more than welcome, and support or challenge us. And after this user consultation meeting, there's then a down selection by ESA of up to 2 missions that will enter phase A. And phase A will approximately 1.5 to 2 years. And in summer 25, the final selection by ESA of Earth Explorer 11 will be done. More information on what I've shown here and what I haven't shown you find on our webpage, care.eu. And that's it. Thanks very much.